Chapters 4, 5, and 6 deal with Newton's laws and the concept of forces and how that relates back to the kinematics you've learned in chapters 1, 2, and 3. Uh, Put succinctly, chapters 4, 5, and 6 are the why to chapters 1, 2, and 3, how, in relation to the way that things move. Um, so, for example, in chapters 1, 2, and 3, when you were learning about projectile motion, you learned that objects accelerate in a vertical direction continuously, but maintain a constant velocity relative to the horizontal component of their motion. That is something that can simply be observed to be true, and we leverage that as a general rule. The next few chapters then provide a modeling framework through which you can understand why that might be true. Newton's description of mechanics, which is what we're talking about in this class, is valid in the realm of things that are roughly human sized, moving at roughly human perception, meaning visual perception of speeds. Um, and work very well. So basically, anything that you can see outside walking around that's small enough to see, big enough to see, that's moving at a rate of speed that you can kind of comprehend relative to the refresh rate of your eyes, this framework we're about to provide works excellent for describing and predicting how those things will move in different circumstances. Newton's model can be broken down into three basic rules. The first one is kind of the basic overview and what it says. So, rule one is you can kind of categorize this as being inertia, which is the tendency for things in motion to continue moving the way they are already moving. And so, the way this is formulated as Newton's first law is objects at rest tend to stay at rest, and objects in motion tend to stay in motion. Traveling in straight lines with constant velocity unless, this is the key detail, acted upon by an unbalanced externally applied force or forces, i.e., a net force. Okay, that's a mouthful. We can simplify that to say the following. When F net is equal to 0, which is a vector, A is equal to 0. So anytime that there's not an unbalanced force or set of forces that are unbalanced, objects do not accelerate, which is tantamount to saying they travel with a constant velocity. If that velocity is already 0, i.e. at rest, they stay at rest. If it's not 0, then they continue to travel with the velocity they already have in the direction they're already going. The only times that is not true is if F net is not equal to 0, in which case objects will accelerate. And so we can take this both directions, meaning if we observe an object to be accelerating, we can infer that a net force or an unbalanced set of forces must be acting upon it. And if we know an unbalanced set of forces acts on an object, then we know that that object must accelerate. Moreover, the direction of both of these vectors will be the same, meaning if I have an object and it's accelerating that way, then I can infer that the object must have a net force acting on it that points that way. So that's the first law. Second law. Second law allows for quantitation. How do we figure out how big forces are? And the way this could be done is if we jump ahead a little bit to a spring force, which is one of the ones you will learn about, we can set up a little experiment that you could do. And so you can have a wall with a spring and an object attached to the end of it that is at rest at some position. That's its equilibrium position. That's where the spring wants to be. What you can then do is compress or expand the spring. So we'll go with compression. And what you will learn is when you compress a spring from its equilibrium position, some delta x, that the further you compress it, you will create a spring force pointed in the other direction. And that spring force will get larger in proportion to the amount that you deform the spring. And so what you could then do, like you're doing already, those of you taking lab courses, is you could do a video capture analysis. And what you would have to do is you'd have to record this displacement distance, which would then be proportional to the size of the spring force applied to this object. And then you can release the object from whatever force is compressing, used to compress the spring, and record its resultant motion. And from your analysis of its kinematics, you can then determine what its acceleration is as a function of different applied forces. And what you would find if you plotted those results, if you plotted the acceleration that you observed as a function of the spring force applied, and if we neglect any other forces, then the spring force in this case would be equal to the net force applied to the object. What you would find is that you get a linear relationship. So the external force applied to an object scales in direct proportion to the acceleration that is caused in the object. Now, if you took it a step further and took this object and took it over to a scale and measured its mass, so this is a scale measuring mass, and then you had several objects, and you could then take several different objects with several different mass and put them on the end of this spring, you could do the same experiment with several different objects. And if we ignore the interactions with the floor here, then what you would see is that for different mass objects, you would maintain this type of proportional linear relationship, but the slope would change. And it would change in such a way that when the object has less mass, so m small, sorry, m big, so when the object has more mass, the acceleration that you get as a result of a certain force applied to an object is lower. And when the m is small, the acceleration you get for that same applied force is bigger. And so if we put it together, all of the variables at play here, what you'll find is that the acceleration caused in an object will depend on the size of the unbalanced force applied to it. That's the direct proportion, right? As F gets bigger, A gets bigger, divided by the mass of the object. We can see that as M gets bigger, your acceleration gets smaller, and as M gets smaller, your acceleration gets bigger. This, in equation form, is Newton's second law. So that is the quantitative relationship between how things move, how they accelerate. That's what happens as a result of what is done to them, which is net forces are applied to them. All of this brings into question, what is a force? So what's a force? And the answer to that question, it's not necessarily physically, uh, doesn't necessarily feel good, but it's a push or a pull. And it requires an external agent must exert the push or pull onto the object experiencing the force. So that's what a force is. Um, might be hard to kind of put that into mathematical terms, but it's something that we can all intuitively appreciate. This is something that we have one of our 5 built-in senses turns this into something that our brain interprets continuously, right? So you feel pushes and pulls. When you stand on the ground, you feel a pressure on your feet. When you push a wall, you feel pressure from the wall, etc. So we intuitively have an idea of what a force is. We see the experiment by which you can get this Newton's second law. So that just says if there's an unbalanced set of pushes or pulls on an object, that object will accelerate. It will accelerate in inverse proportion to its mass. The third law, so law 3, what that says is this is always a two-person dance, so it takes two to tango, which we already kind of qualified up above in the second law when we talk about what a force is. You need an external agent, that's a thing, to apply a force to some object experiencing that force, right? So that's an object. So that means you always need two things to have a force ever, one applying it, one experiencing it. And what this third law says is if object A applies a force on B, then necessarily object B will apply the same force back on A, but in the opposite direction. And so one of the things we're going to start doing in this chapter is come up with ways to visualize forces and how they act on objects. And that's going to be something called a free body diagram. And so a free body diagram involves making an object and identifying it as a point, representing it as a point rather, and then summarizing the forces as vectors emanating from that point. So if this is object A, then we might imagine that object B is pushing it to the left. Well, then in that case, once we know that, if we have this type of situation, we can identify that this is an action-reaction pair of forces. Then if object B pushed on object A with a certain size vector to the left, then for object B, we must have a force acting on object B that's the same size in the opposite direction due to object A pushing back on object B. And that's Newton's third laws. And from just these three laws and the existing knowledge of kinematics, we can work out everything that is to follow in the next three chapters.